So, in the previous lecture, we had looked at how to do the numerical integration for an element. In fact, we had outlined a general way of doing the Gauss-Legendre integration. One could choose a different integration rule. For example, there is another integration rule which is available, which is called the Gauss-Lobato. But that is generally not used. This has its own features. Okay. So, what we had said is, fine, if we can fix the integration rule for an element based on the order of the integrands involved, then now we can do the element calculations. So, here we are going to concentrate on how to do the element calculations. For a generic element I k. So, for the generic element I k, you will have the stiffness matrix K for the element and the load vector F for the element. We would like to get the entries of this element stiffness matrix and the element load vector. Okay, so before we go and do the process by which we will obtain the entries of the element stiffness matrix and the load vector, let us fix certain ideas. Fix essentially what we want our finite element program to do. So, from the finite element program, we want the following things to be finite element program. Yeah, we want the following things to be possible to handle. 1, we may have domains with different material coefficients or material constants in different parts of the domain. So, we may have, let us say this is a point x0, this is a point x1. Okay. In this, it is the material constant is piecewise linear. Here EA is piecewise linear. Here EA is constant. Here also it is linear. So, as far as our EA is concerned, we will say that this is at most piecewise linear. Second thing that we would like to do is, given a bar, we would like this bar to also lie on an elastic support. Which is a continuous elastic support, and it has constant, elastic constant Kx is a constant piecewise. So, we can imagine that in a particular part of the bar, I have the elastic support, in the rest of it, it is not. So again these will be demarcated by some points, let us say x2, x3. So next what we want is, as far as the force is concerned, the distributed body force, again let us have the bar, over which I am applying this distributed body force f of x. Okay. This can be, f of x is piecewise quadratic at the most. Now if we are really interested in making our code a little bit more general, then we can also do the following, that to this bar, it need not be of uniform cross section material, I will also apply these point loads in the interior, P1, P2, these are point loads. So we see that this is what we want our code to be able to handle. So with this in mind, in an element, so if I take a generic element ik with endpoints xk and xk plus 1, now I know that in the element your EA of x is some constant plus some linear at the most. The spring stiffness is a constant in this element, and f of x is at most a quadratic given by this data. These values of the coefficients f0, f1, f2, k0, c0 and c1, these are all going to be input. They should be available to us as known data. Okay. Now this f0, f1, f2, k0, c0, c1 has to be obtained piecewise, which will come from somewhere. So using this information, now we can go ahead and do the element calculations. So let the order of approximation, which we say is going to be fixed for the full domain, be given as P. What do I do first as far as element calculation is concerned? I am going to take this element matrix K and the element load vector F, and I am going to initialize it. That is, I am going to set the values of all the entries of K and F to 0 before I start doing anything. Then, since xk and xk plus 1, the two coordinates, two endpoints of the element are known, they will be available to us. So we can find the size of the element is equal to xk plus 1 minus xk. Given the size of the element, we can find the size of the Jacobian is equal to hk by 2. Okay. So, I am following the steps in the way you have to do things in a computer program. Then what else do I do? So, given P, I will define the number of degrees of freedom in the element is equal to P plus 1, and I give it a name end of. What else do I need to do? So, given this end of, given the size of the element, given the j, now I start loop over the integration points. Okay. Once I start the loop over the integration points, then for each integration point I start the loop over the degrees of freedom of the element. In this loop I am going to do the following. I am going to say Fj is equal to Fj plus, now I am going to do the numerical integration to find my load vector entries. So, I take the jth load vector entry, to this I am going to add the contribution due to this particular integration point. So, it is going to be f of x at the point psi I, okay, into psi dot for the ith point and the jth location into, so these two things are there, then I will multiply with w corresponding to the ith point into the Jacobian. Now, here if you see this x of psi I, how will I get this f x of psi I? So, this part, for this I am going to now add these extra bits here. So, for the integration point I am going to compute x is equal to xk into 1 minus psi I divided by 2 plus xk plus 1 into 1 plus psi I divided by 2. This gives me the physical coordinate corresponding to this integration point. Given this x, I also need to obtain f of x. So, I will obtain it from some routine called load data. So, to which I will pass the x and it will return me f of x. So, this is the routine. So, what I do for each integration point, I find the physical coordinate corresponding to this master coordinate. At that physical coordinate, I take that value, pass it on to this load data routine, which should for this element return me the value of the distributed load at this point. That I put it in here, multiply by the value of the shape function corresponding to this point into the weight function into the Jacobian. So, this is all I have to do as far as the load vector calculation is concerned. Then, for the stiffness calculation, Again I have this loop over the degrees of freedom, and here I am going to say that k j k. So the entry corresponding to the jth row and the kth column of the stiffness matrix for the element is given as k j k, that is the previous value that I obtained, plus the part due to the EA. So EA at this point x into the derivatives of the shape functions. So I will have psi dot for the ith point into the weight corresponding to this point. Now what? Remember, this was multiplied by 2 by hk, so that will be 1 by the Jacobian. This is the part due to the material as such. Now the part due to this distributed spring which is attached, if it is there in the element, so it will come out to be k0 into Wi and multiplied by, now this part is multiplied by the Jacobian. So this, now you end loop over the k, end loop over the j, end loop over the I. So if I do this, I have obtained the entries of the stiffness matrix. Again the question is, I need this and I need this. So for this, what should I do? I should go back up there, and here after I compute x, I call load data. Here I also call material data, which will take the x, return me the value of EAX and K0. So I will have to call for the particular x both the load data subprogram, which will return the value of the force F of x at this point, and also the material data subprogram, which will return the value of the EA and the K at this material point. So I do this integration, and my element stiffness and load vector is ready. So this is ready. This is all we need to do as far as these element calculations are concerned. Now one thing that you should do in order to avoid making errors while programming is some features of your programming. Your program should have a nice flow. Secondly, in your program, proper indentations have to be used. What do we mean by proper indentations? If I go back and I look at these loops that we had introduced, one loop over the integration points, the other loop over the one loop over the integration points, the other loop over these degrees of freedom, and the next loop over k. We should have the embedding of the loops coming out clearly through an indentation of the statements. Okay. So, if this loop was the innermost loop, so it is embedded indented the most. So, if you have this kind of a structure, and in the end we see that this indentation also comes out as far as the ending of the loops is concerned. So, it becomes very clear that you have which loop is embedded inside which one and where the loops have ended, because otherwise it can lead to problems. The other thing that we have to do in all these programs for clarity and ease of reading and ease of use, have verbose, very verbose comments in the program. Okay. So, once all these things are taken care of, most likely the program that will come out, the routine or the subroutine, will be error free. So, what I would like is to name these element calculation routines as element k. So, this is my name of the routine. You see that I would like to give names which are relevant. That is, I cannot call a subroutine which does element calculations by something like epsilon, delta, and so on. Similarly, when I have these variables, the variable names should not be arbitrary. They should reflect what they really correspond to. So, if I am talking of stiffness, I should write it as k or k stiff. I can use more words. If I am talking of load vector, I can write it as x load or f load or something like that. Shape function, psi, EA, material constant, k, we can say k spring as kx and so on, all those things. So, these namings should be properly done. Okay. So, our element calculations are over. Now, as an exercise, you should try to write this program, write this subroutine. Okay. Now, as far as the full-fledged program is concerned that we would like to write, what are the other things that we need? So, we have specified that as far as the material is concerned, we would like to have piecewise linear material, the EA is piecewise linear, K is piecewise constant, the load is piecewise quadratic, and I can have point loads. Similarly, the P we said the order of approximation is going to be uniform throughout the mesh, throughout the domain. Okay. We would also like to fix what kind of boundary conditions we would like to impose. So, what kind, till now I have not been very general in what I did. So, we would like to have certain types of boundary conditions. So, let us look at the candidate boundary conditions. At an end, let us say a particular end, I can give you a force, I can give you a displacement, it can be built in or some specified value. So, u is specified, or I can give you the force in terms of the displacement, that is, this is a spring with constant, some constant k bar and an initial compression delta L. Okay. So, if I look at this spring, this is at the end x equal to L. Here you will see that P is equal to minus k bar into delta L plus u at L. So, the spring here, the load, the end load is actually in terms of the end deflection. Okay. So, all these cases we would like to have. So I would like to have this one. So this is a Neumann condition. This is a Dirichlet condition, and this is a so-called Robin condition. Okay. These things also we would like to have in our code, and according to the user's desire, I should be able to apply at each of these ends. What I did at this end x equal to L can be done at the end x equal to 0 also. Whatever I choose I can do. For example, I can have this kind of a situation here. Here k bar, it is k bar at L, let us say this is k bar at L, k bar at 0, you can have an initial compression delta 0, okay, and at this end I can have an end force P. So I can have any combination of the two things, okay. So that will decide what boundary condition I would like to apply. So the boundary conditions that we want are of this type. Another feature we would like to have in the code is something that we will discuss in the future. So I have now somehow obtained the global matrices K and the global vector F. So I would like to now solve it to obtain the unknown coefficients U. Okay. So how do I solve? So to solve, there are various ways of solution, and those can be classified into two broad classes of families, so called direct solvers and iterative solvers. In the direct solver, I try to essentially do elimination to obtain the solution U directly. In the iterative solver, I start with a guess value of U and I try to minimize the difference between Ku minus F, that is called the residue, till I converge to the solution. But here we are not going to look at the iterative solvers, we are going to look at the direct solvers. And in the direct solvers, we are going to look at very simplistic direct solvers, two types, which are based on the Gauss elimination and something called the LU decomposition. So we will outline the algorithms for both of these processes. Yeah. Now one should also be aware that these things are available freely on the net. So there is really no need to go and write these solvers by yourself. There are some websites, for example, there is a website called netlive.org, which has a huge repository of linear algebra routines. In fact, it has all sorts of programs available, the source codes are available. So one can download these things for Fortran and C, Fortran 95 and all those versions from this website. So this is a very useful website from which these solvers can be downloaded. In fact, better solvers can be downloaded which essentially take advantage of the sparsity of the stiffness matrix, or the fact that the stiffness matrix is banded. Okay. So let us now recap as to what it is that we would like our program to do. Okay. So program to do, first thing we said that these are the input data which we wanted to specify, we have specified. we have specified what boundary conditions can be applied. Now I obtain a solution using this solver. So this solution has to be interpreted. How do we interpret the solution? So we would like to know various things. The value of u of x, Eax, du dx at points, simply du dx at points. Okay. So given a point, I would like these values, or I would like to have a plot of these things. So I would like to have, for example, u is there, x is here. So I would like to have a plot like this. Okay. So we would like to use our vector u to construct the solutions u or these quantities wherever I wish. So this comes under the category of post processing of the information that is coming out of the finite element computation. There are other things that the finite element data as such, the finite element solution will give us these forces which are not continuous, which are jumpy in nature. So we would like to somehow smoothen these out to get better values of the resultants of axial force. Okay, with this I will now like to outline the basic structure of the finite element code, the one dimensional finite element code that we are going to write. Okay, so our finite element program will have three basic modules, the bigger modules. The first module of the finite element program will be called the preprocessor. It will be called the preprocessor that we have here. Now in the preprocessor, what are the things that we are going to do? So in the preprocessor, first thing that we do is we go and initialize all the global matrices. Okay, so we'll initialize all the global matrices. What are the global matrices that we have? So the global matrices that we have are the global stiffness matrix K and the global load vector F. That has to be initialized. Then we have our vector which gives us the coordinates of the points in the mesh or the nodes, these coordinates. The vector of these coordinates is also has to be initialized. Okay. Then our integration points vector has to be initialized, our weight function vector has to be initialized, and then our these arrays which carry the values of the shape functions at the integration point and the derivatives of the shape functions at the integration point have to be initialized. It is always a good idea to initialize all the global matrices, arrays and vectors right at the beginning of the program. Also, if I am using C or other things, all the global variables have to be initialized too. Okay. After we have done that, then we have to read the input data. What are the input data that has to be read in? First is the material data, that is, okay, tell me how many material domains is my mesh broken into, and for this material domain, for each of the material domain, so I may have these many partitions of the domain, and in each material domain give me what are the material properties. So how are the material properties given? In terms of the coefficients of the EAX, that is EAX is equal to C0 plus C1x in a particular material domain. So in each material domain these values have to be given. Similarly, the K0 has to be given in each of the material domains. Similarly, I will have to give the load data, that is the distributed load. How is it varying? Is it varying in the whole domain as a linear quadratic constant, or is it applied piecewise? In a small region it is something, in the other region it is something else. Everything has to be given upfront. Boundary condition. At the two ends, each of the two ends, what type of boundary condition is applied? For example, at this end x equal to 0, I may have a Dirichlet type boundary condition, or a Neumann type boundary condition, or a Robin type boundary condition. For each of these boundary conditions, I have to give the value of the corresponding parameters which are needed. For example, if it is Dirichlet, then I have to give you what is u at 0 as an input data. If it is Neumann, then I have to give what is the tensile force at this end. If it is Robin, then I have to give the spring constant of the attached spring and the initial compression of the spring. So this has to be done at both the ends, and all that information has to be read in from an input file into our program. Next, given all these things, also I may be having this point load data, that is there are certain points where I would like to apply point loads. Now this list can be endless. We will have to restrict ourselves to only a specific class of problems that we would like to handle as a sample case. Mesh, for example, we may take the mesh now to be made region by region. Why should it be like that? Because the mesh has to honor the material domains. So the boundaries of the material domains, it has to, I know that at a point where a point load is applied, I have to have a node. So these things, this information has to be built into the code. So when I make the mesh, for the mesh I have to give the information as to what are the boundaries of each of the subdomains over which the meshing has to be done. And then over each subdomain I have to say how many subdivisions we want. So let us say that in each subdomain we want uniform meshing. So let us say in the first subdomain I want 5 subdivisions, so it will put 5 uniform elements here. In the next subdomain I may want 2, so I will tell 2, it will put 2 elements, and accordingly it will construct, it will create these nodes which will be stored. In the third one I may have 4 elements, so it will accordingly put the nodes which will divide this piece into 4 elements. Okay, so let us take that example of a domain like this. Where I may have in this region the distributed spring support. Okay. I may have a distributed force of some intensity in this region, and I may have some other intensity in this region. Okay. Further, I may have point loads somewhere here. P1. So as far as making the mesh is concerned, I will have the first subdomain is this one, going from point x equal to 0 to some point x1. The second subdomain, so this is the subdomain where my load is distributed load is applied, and here it ends, so the load changes. The next subdomain will be this one, which will go up to the point x2. So here what happens, the material is one type, but here it is changing, that is the cross sectional area is changing. So I have to honor that. Third subdomain is this part where we are in this constant cross section part, but there is no distributed spring. So this will become my third subdomain. Now the fourth one, you see that here the distributed spring is there, but there is a point load here and I have to honor the point load. So the fourth one is this x4. Then the fifth one, so from here I continue, I see that this is the end of the region where the distributed spring is applied. So this becomes x5. This continues till this one, where again the area changes as x6. Now by coincidence I have taken the distributed load of a different type, but coinciding with the whole subdomain here. So for that case, so all these interface points, all these transition points, due to various reasons, due to material, due to the load and etc., have to be clearly specified in the input data, and then the meshing has to be done piecewise. So this we will take care of in a future lecture, but this has to be honored. If I don't do this, our whole computation may give us faulty results which are not very good. And this information is also true for 2 and 3 dimensions, where we have to honor the material boundaries. So as far as the mesh is concerned, we have to honor those subdomain boundaries which come in due to the load data, etc. Okay. Approximation order we are going to fix for the element, for the whole domain. We will assume that the approximation order is the same. So after doing this, after getting all this input data, we will now make the mesh. That is, in each of these subdomains, we have to now put elements of some number of elements as we desire. Now here we will have to generate some information called the element node connectivity information, that is, which are the nodes which form the extremities of the element. So here that is very simple, because for element ik, I know that is given by the nodes xk and xk plus 1. So that is not a very big problem, but this is a feature which should be added in the finite element program, because in 2 and 3 dimensions this becomes very important. Then the other thing that we have to do is, okay, we have formed a mesh, we have read all the input data. Now given the approximation order, we have to construct the degrees of freedom over the elements. You know that given P, in an element there are P plus 1 degrees of freedom. So we will have to do this construction over the whole domain, that is, we will have to construct the basis functions. So what do we mean by construct? So to each element we will have to assign which are the global basis functions which correspond to the local degrees of freedom in the element. This is called the global to local enumeration, and this is a feature which will be there in any dimensions that you work in, 1D, 2D or 3D. Now the next thing is we have to create. So we have constructed the mesh, we have constructed the approximation information. Now we have to create the integration points and the shape function information, for which we have already seen how to write the respective subroutines or subprograms. Then, so this was the whole body of the preprocessor. Essentially the preprocessor gets us ready to go and actually start doing the actual computations with respect to the problem at hand. So then we go to the processor. Processor is the heart of the program, where the whole element calculations are done and the element stiffness and load vectors are created. Here the element stiffness and load vectors are created. Now these are passed to some place where these element calculations are assembled to get the global stiffness and load vectors like we had done in an earlier lecture. Now, how do we assemble in a computer? By using this global to local enumeration. So, this global to local enumeration array or a vector will tell us which global locations should our element entries go into. So, we will go and pick the right row and column in the global stiffness matrix and the right row in the global load vector, where I will go and add these element contributions. So, this is the process of assembly. So, after my global stiffness matrix and the load vectors are assembled, then I will apply the boundary conditions at both the ends. What does that lead to? Application of the boundary conditions, it will either lead to a modification of the stiffness matrix. How? If I have the Dirichlet boundary condition, then I have to enforce that the value of the solution at that particular point is equal to the given value. That is done by doing suitable modifications to the stiffness matrix, as we had done in one of the assignments earlier. Similarly, the load vector also has to be modified. If I have a Neumann condition at an end, then I have to go and add the effect of that end load applied to the global load vector. If I have a Robin boundary condition, then I have to go and modify both the stiffness and the load vector entries. Why stiffness? Because from the Robin you see that the load, the end load comes in terms of the unknown end force. Unknown end displacement. So, that unknown has to be brought into the stiffness matrix contribution. So, for all these cases we have to appropriately modify the global stiffness matrix and the load vector to account for the applied boundary condition. Once I take care of these things, then I go and solve the final system Ku is equal to F, find out what are the displacement vectors U. Now, displacement vector U essentially corresponds to the coefficients of our series representation of the approximate solution. If you remember that U approximate was Ui phi I. This we have to always remember that this is going to be true irrespective of what we do. So, once I have this representation, now if I have these coefficients, now I have essentially the whole approximate solution. In the whole domain, wherever I need the solution, I can go plug the value of the x, I know the coefficients, I will get the u. It's as simple as that. Now, we don't have to do this per se. How we will do? We will say, okay, which element I want the information in. In the element, I know only the element shape functions are the active phi's, all the other phi's are 0. Okay. So, we will take those element shape functions, multiply by the suitable coefficients ui, and we get the u in the element. Take derivatives, we will get the derivatives of u in the element. Okay. From this, we can construct all the information we need for in order to display the response characteristics of the component loaded by certain loads. This part of displaying and using this displacement vector that we have computed to get some meaningful response quantities goes into the third big module, which is called the post-processor. In fact, post-processor is the most colorful part of the whole program, but it doesn't do too much. The bulk has been already done. So, in post-processor, we try to get what we would like to get is obtain stress information at points in the elements. Good points are the so-called Gauss points, which are the integration points. We can give the direct values of the derivatives and the stresses or the axial forces, or we try to do some kind of smoothing or recovery through which we claim to get better values of the stress information. We can obtain displacement values at desired locations like maximum displacement, displacement at a joint where two dissimilar materials are present, interface of those. We can plot the data, we can use various plotting algorithms which are available freely to plot the graph of the response. We can have the graph of the displacement, graph of the slope, graph of the axial force. All this information we can have plotted in the post processor. That we can create various kinds of color pictures, which essentially forms the body of the post processing part of the code. Once we have these three modules ready, we have our finite element program. So in the next lecture, what we are going to do is we are going to look at now pieces, the remaining pieces of the modules. Remember that the integration, the shape functions, and the element calculations we have already done. How do we fill in the rest of the part? That is making the mesh, then creating the degrees of freedom information, then this global to local enumeration, then applying the boundary conditions, and so on. Solver, okay, we'll talk of those. We'll talk of a simple post processing scheme to get better, so called better recovered stress information, and then the program is essentially ready. Thank you.